Hi guys, in this lecture we are going to talk about light and waves and the relationship between these two phenomena. Let's start off by talking about something that many of us have direct experience with, visible light. So we all know that visible light comes in a variety of different colors, all the different colors of the rainbow, illustrated right here. Okay? So it turns out that all of these different colors of light are in fact different types of what we call electromagnetic radiation. So as the name implies, electromagnetic radiation consists of both an electric and a magnetic component. And if we look at what's actually happening here, right, if we have light traveling in a certain direction, what we see is an electric field here illustrated in red that's oscillating, going up and down, kind of like a wave, and another magnetic field illustrated in blue going forwards and backwards, forwards and backwards, forwards and backwards. So both an electric and magnetic field oscillating, and they're oscillating at a 90-degree angle. They're perpendicular to one another. And that oscillation itself is perpendicular to the direction of travel. So as this illustration points out, if we want to really explain and understand what light is, we're going to have to start looking at wave-like phenomena and understanding waves. So to a first approximation here, waves are fairly simple. Okay, we basically can describe a wave as this sort of oscillatory behavior. We can describe this wave using a wavelength, okay, illustrated here, which is basically the distance between 2 points of the same amplitude on the wave crests. Right? So in this case, oftentimes it's easy to pick, say the highest point that the wave goes, keep following the wave down, follow it back up until it goes all the way back up to its highest point, and measure the distance between those 2 points, and that's your wavelength. And then the amplitude is how high that wave goes when it reaches its maximum height. Now notice, amplitude is going to have to be measured by looking at that highest point, or of course you could do something like this and look at the very lowest point, but it has to be taken at one of those high or low points, right? Whereas wavelength, we could obtain the same value for wavelength by looking at any 2 points on that wave, as long as we make sure to take that same amplitude. Okay, now it turns out that by understanding these two concepts of wavelength and amplitude, we can already start to understand some key properties of light or electromagnetic radiation. So it turns out that different wavelengths of electromagnetic radiation have different colors. So if you have a relatively long wavelength, denoted here by a lambda A, and you compare that to a shorter wavelength, say lambda B, well, it turns out that, say, if you've got a red color light, visible light in the red portion of the spectrum of the rainbow, right, that wavelength is going to be longer than the wavelength associated with, say, yellow light. So we're going to have a lambda A is going to be greater than a lambda B. Similarly, if you go to even shorter wavelengths of light, say a lambda C here corresponding to blue light, you have an even shorter wavelength. And I drew that the wrong way. So the lambda C here is going to be even shorter than lambda B. Okay, so different colors correspond to different colors of visible light. Now the amplitude also has a direct correlation to something that many of us perceive. So if you have, say, dim light, light that's just simply not as bright, then that corresponds to a lower amplitude, whereas bright light corresponds to a higher amplitude. And remember that amplitude is denoted by just the distance between that axis along which the light is traveling, and so direction of travel here, and the highest point on that that wave crest. Okay, so these are our first two properties of waves: wavelength and amplitude. Now there's going to be one more property that we are going to find very useful in a number of applications, which is frequency. Okay, so frequency is a little bit more challenging to understand, but it's not too bad. So basically, the frequency is defined as the number of wave crests that pass through a stationary point in a given period of time. So we're oftentimes going to use this Greek letter nu, which I've written out here for you guys, to denote the frequency. So notice the axis now. The x-axis here is a time axis. So when we compare the red and yellow visible light, the red and yellow forms of electromagnetic radiation, we can see that in the case of the yellow, there are going to be more wave crests that pass through any given stationary point per unit time. So there's more and more of these crests showing up. Therefore, the nu for the yellow here, for B, is going to be greater than the nu, the frequency of that red light, denoted by A. Okay, so these are our three properties. If you're dealing with light, we can characterize those the wave, that electromagnetic wave, by these three properties: wavelength, amplitude, and frequency. Now, it turns out that these concepts are even more powerful. This goes beyond the visible light spectrum that we all directly perceive. Right? In fact, there's a vast electromagnetic spectrum that's illustrated right here that encompasses all different forms of electromagnetic radiation. So way down here at the very long wavelength side of things, we've got radio waves, right? And if you start moving to the right and follow to the right, we're getting progressively shorter wavelengths. We're going to hit the microwave region, and then we'll go into the infrared region, and then this tiny little piece right here is that visible light spectrum. And then you go to even shorter wavelength light. We get to the ultraviolet, then X-ray, and ultimately to gamma rays. Now this is kind of an eye-opening figure to see. It turns out that the electromagnetic spectrum that we are designed to be able to detect is only a small little region in a vast spectrum of electromagnetic radiation. And each form of electromagnetic radiation, perhaps you've heard about this in various contexts, from everything from heating up your food to medical diagnostics, right? We see different forms of electromagnetic radiation and their corresponding properties being useful and applied in a vast array of different settings. And so we'll go into some of those as the course progresses. For right now, I want to look a little bit more closely at some of the other axes on this diagram here. So we followed our wavelength, basically decreasing wavelength, going from very long wavelength radio waves all the way down here, the really short gamma rays. But notice that there's two other basically variables included right here on the plot: energy and frequency. Okay, so now let's take a moment to essentially explore the relationship between wavelength, energy, and frequency. And in some sense, we know the answer, right? By just looking at this figure, we can see that when you have really long wavelengths, we're going to have relatively small frequencies and relatively low energies. When you go to really short wavelengths, we go to relatively high frequencies and high energy. So basically, our job now is going to be to really quantify these relationships. And it turns out that Einstein's going to help us out in this regard. So there's a really cool principle that Einstein figured out for us, which is this idea that the speed of light in a vacuum is always constant, and so it's always a fixed value. And we typically use c to denote this fixed value of the speed of light. So it turns out the numerical value for the speed of light in a vacuum, a relatively long number here, 2.99792458 times 10 to the 8th meters per second. Now, think about this for a second. This is a very fast velocity, okay? When we're talking about, something on the order of 10 to the 8th meters per second, what we're basically saying here is that if you have a light wave, okay, and you want to see how far that light wave can travel in, say, 1 second, right? The answer is given by this large number, almost 3 times 10 to the 8th meters. Okay, so that light is going almost 1 billion meters, just under a billion meters in 1 second. So light is very, very fast. So even though it's set at a fixed speed, right, that speed limit is relatively high. Now, the fact that that speed is a constant value allows us to find a really nice and simple relationship between the wavelength and frequency. So it turns out that our first equation for this section is C equals lambda times mu. Speed of light is equal to the wavelength times the frequency. And just to make sure that these units are working out, if we explore what, the units, and using meters and seconds as our measured variables here, lambda, a wavelength, right, is a length. We could measure that and say meters. And frequency has units, as we saw previously, of inverse seconds. So if we multiply meters by an inverse seconds, we get a meters over seconds, which is, of course, the speed. And Einstein even gave us more helpful information. Right? Einstein gave us a very nice relationship that we're going to be exploring in more detail later on, which basically tells us that the energy of any form of electromagnetic radiation can be directly related to the frequency using a constant. And I'll have a lot more to say about this constant in the coming slides and the coming lectures. Suffice it to say, it is a constant. And so given the relationship up here, C equals lambda times the frequency, we can solve this equation for frequency, and we can see frequency is going to be equal to C over lambda, and we can use that to obtain another form of this energy expression, which allows us to predict the energy given a certain wavelength of electromagnetic radiation. So now if we go back to our electromagnetic spectrum and we keep these equations in mind, now we can get an appreciation for these trends that we drew out before. So really long wavelengths are going to give a very large denominator here, which is going to correspond to a relatively low energy. And of course, mu is C over lambda, so that large denominator for that wavelength is going to give rise to a relatively low frequency up here on this left-hand side of the spectrum. And of course, conversely, if you go all the way over here and you start going to very, very short wavelengths, well, you've got a very, very small denominator then, which is going to cause that energy term to increase. So the energy of that radiation increases as you go to the shorter and shorter wavelengths. And similarly, using our expression for frequency, we're going to see an increase in the frequency corresponding to those progressively shorter and shorter wavelengths. Now, I want you guys to go ahead and memorize the relative ordering of these different types of electromagnetic radiations. In other words, I want you guys to be able to answer questions, without your notes, that look something like this. So here I'm asking you to arrange the following types of EM radiation: visible light, X-rays, and microwaves in the order of increasing wavelength, frequency, and energy per photon. Okay, so for the first one, for wavelength, we know that this far left-hand side of the EM spectrum corresponded to relatively long wavelengths, and as you move from left to right, you get relatively short wavelengths, short lambdas. So basically, we need to come up here and rank our 3 different types of radiation in order of increasing wavelengths. So we're going from the shortest wavelength to the longest wavelength. So we come over here and say, well, which one of these, visible, X-ray, or microwaves, has the shortest wavelength? And well, of course, it's going to be that form of radiation that's the furthest to the right. So our X-rays are going to have, the shortest, wavelength, followed next by visible light. And remember that little sliver of the EM spectrum right here. And then finally, microwaves is even further to the left. Okay, now if we look at frequency of course, follows the other direction, right? So remember, frequency starts off relatively low on the left-hand side, and you get higher and higher frequencies as you go from left to right. So now we're going to flip the order of these forms of electromagnetic radiation. Low frequency is going to be here with the microwave, followed by visible, and then X-ray. And of course, lastly here, energy per photon. Given Einstein's relationship here, we know that energy is directly related to the frequency. So of course, the energy increases as you go from left to right. So the ordering of both energy and frequency are going to be the same. So to sum things up here, what we've seen is that, first off, light, visible light, is a form of EM, electromagnetic radiation, right? And I want you to be familiar with that entire EM spectrum. You don't have to remember individual values, but I want you to be able to certainly be able to list out the relative ordering of the different forms of electromagnetic radiation, radio waves, microwaves, and the like. And remember, we've got this set of relationships that allow us to describe these different types of light, right? So we've seen that this electromagnetic radiation is these oscillating electromagnetic fields, and the amplitude of these oscillations, the frequency of these oscillations, right, and the wavelength of these oscillations are all important characteristics that help us to understand the different behavior in these different types of electromagnetic radiation. We've got some really useful equations that we're going to be seeing a lot of as the course moves on. So we certainly want to have those hammered down as well. And with that, I'm going to go ahead and direct you guys to the first set of sample problems that I'll have you guys work through before you go on to the next video.